If aliens looked at us, the tiny clue we'd leave behind if an alien civilization, 1,000 light-years away, pointed a powerful telescope at our sun, what microscopic clue in the light would betray that Earth is here at all? From that distance, our planet would be utterly invisible. Just a pale, drowned speck lost in the glare of a star. No shining blue oceans, no city lights. Not even the faintest resolved disk. To those hypothetical observers, the sun would look like a single bright pixel, and yet, hidden inside that pixel, there would be a secret. They would not see Earth directly. Instead, they would have to watch the sunlight itself. They would measure how its color and brightness change, photon by photon, year after year. Perhaps they would notice that every 365 days, the sun's light dims by less than 1 part in 10,000 as a small world slips across its face. Perhaps they would see an almost imperceptible wobble in the star's motion, as if something tiny is tugging on it from one side. This means the only way to find us, from that far away, is to decode those faint fingerprints in starlight, to turn a flicker into an orbit, to turn a wobble into a planet. It should be noted that this is exactly the challenge we face when we look outward into the Milky Way. The planets we seek are not bold, glowing beacons. They are, by design, hidden. In the hunt for alien life, this is the central problem. We want to know whether we are alone in the universe. We want to know if other Earth-like worlds circle distant suns, perhaps with their own oceans, their own skies, maybe even their own biology. But while the majority of us feel that life must be out there somewhere, it is far harder to show where, using only the light of a distant star. Our entire answer to that ancient question depends on how well we can read those clues. If we misinterpret a flicker, we invent worlds that are not there. If we overlook a wobble, we miss entire systems. Optimistically speaking, every improvement in our methods is another chance to reveal a real, habitable planet. And here's the mystery. A few decades ago, we had no confirmed planets beyond our own solar system. 0. Today, we have a catalog of thousands. Hot Jupiters skimming their stars, super-Earths hugging red dwarfs, worlds in and out of the Goldilocks zone. So it's time to find out the truth. How did we get from nothing to this astonishing menagerie so quickly? So, let's begin. In this episode, we will follow the full journey, from early false alarms and bizarre first discoveries, through the main techniques that let us weigh and measure unseen planets, to the moment we started reading their atmospheres and planning the search for a true Earth 2.0, because somewhere out there, another civilization may already be doing the same to us, why finding other worlds is so hard and so important. But before we can follow that journey, we have to face an awkward question. If planets are everywhere, why was it so hard to find even one beyond our solar system for most of human history? On the surface, it sounds simple. Point a telescope at a nearby star, zoom in, and look for a tiny Earth-like dot. In the hunt for alien life, that feels almost obvious. But while that picture is intuitive, the physics is brutal. In visible light, a typical planet is roughly 1 billion times dimmer than its star. That is like trying to spot a firefly hovering next to a stadium floodlight from thousands of kilometers away. This means that direct imaging is one of the hardest things we can attempt in observational astronomy. The star's glare washes out the scene. The planet is not just small, it is dark, lost in diffraction patterns and detector noise. Even with our best instruments today, we only directly see a handful of giant worlds, far from their stars, under almost perfect conditions. Anything like an Earth in a tight, warm orbit is essentially invisible, yet the stakes could not be higher. Are we alone? Is our solar system a typical planetary system, or some cosmic oddball? How many worlds sit in that delicate Goldilocks zone, with the right temperature for liquid water, and maybe a stable atmosphere? These are not just technical questions, they cut straight to our sense of place in the universe. It should be noted that, before the 1990s, the situation was strangely paradoxical. Most astronomers assumed other planets existed. The formation of a star from a disk of gas and dust almost begs for leftover clumps to become planets. But while that logic was compelling, we had 0 confirmed examples. Decades of claims. From 19th century hints to Van de Kamp's supposed planets around Barnard's star, all collapsed under better data. So many experts quietly doubted we would ever detect a true exoplanet. The signals just seemed too small. How do you prove that a tiny, dark companion is there when you cannot see it directly? You look for what it does to the star. That is the core technical challenge. We are trying to infer the presence of these hidden worlds from the slightest changes in starlight, motion, or timing. A planet tugs its star, making it wobble by meters meters per second. A transit blocks a fraction of a percent of the light, sometimes just parts per thousand or even parts per 10,000. A moon-sized world can shift the tick of a pulsar by microseconds. Optimistically speaking, those whispers are just loud enough. So it's time to find out the truth, how we turned these almost invisible signatures into a catalog of thousands of planets. Because the first solid detections did not just confirm one new world, they revealed a universe far stranger than we expected, and the next method in our story would blow everything open. Before the breakthrough, speculation, mistakes, and near misses. Before we talk about triumphs, we have to talk about guesses. For most of our history, other worlds were more philosophy than physics. So, let's begin in the 19th century, when telescopes were just good enough to mislead us in beautiful ways. Astronomers peered at Mars and thought they saw canals, long, straight lines, maybe built by a dying civilization trying to move water across its surface. Were they real? No. They were artifacts of the human eye and brain, connecting faint smudges into patterns. But while the canals were an illusion, they captured something important: the instinct to see planets and the possibility of life everywhere we look. The same mix of insight and wishful thinking followed us into the early 20th century. If a nearby star seemed to wobble slightly on the sky, many assumed the cause must be a hidden planet tugging on it. After all, if our sun has planets, why not every other star in the universe? This means even tiny positional shifts became suspicious. They might be the first hints of alien systems, or just noise. No story captures this tension better than Barnard's star. It is a small, dim red dwarf, only 6 light-years away, racing across our sky faster than any other star. In the 1960s, Dutch-American astronomer Peter van de Kamp spent decades photographing it through the same telescope, measuring its position on glass plates with painstaking care. He reported a periodic wobble. The conclusion seemed irresistible: at least one Jupiter-mass planet, maybe 2, in orbit around Barnard's star. In the hunt for alien life, this was electrifying. A nearby planetary system, detected from the tiniest of shifts. Newspapers covered it, textbooks mentioned it. The idea of a planet around Barnard's star felt almost settled, but the wobble was not in the star, it was in the telescope. When the observatory's lens was cleaned and its optics adjusted, the planetary signal changed too. Later reanalyses showed that the tiny shifts Van de Kamp tracked the instrument's maintenance history, not the gravity of an unseen world. It should be noted that he was careful and sincere. The problem was that the system itself was lying. Barnard's star became a cautionary tale: how subtle instrument systematics, combined with our desire to find planets, can create convincing but false detections. So it's time to find out the truth about our methods. If glass plates could fool us, what else might? By the late 20th century, technology had improved dramatically. New spectrographs could measure a star's velocity to a few meters per second. Electronic detectors replaced photographic film, turning starlight into precise digital data. Yet there was still a glaring absence: no confirmed planets around sun like stars, decades of effort, and nothing everyone could agree on. Optimistically speaking, that silence meant one thing: we were almost sensitive enough. We just needed a different approach. And when the first confirmed exoplanets finally arrived, they did not orbit a comfortable, sun-like star at all. They circled something far stranger, where no one had seriously expected to find planets. The first exoplanets, worlds around a dead star, no warm sun, no gentle Goldilocks zone. So how did the first confirmed alien worlds turn up around a dead star that should have blasted everything nearby to dust? So, let's begin with that dead star. It was not a quiet, fading ember, but a pulsar, the ultra-dense core left behind after a massive star explodes as a supernova. Cram more mass than the sun into a sphere about the size of a city, spin it dozens or hundreds of times per second, and you get a neutron star that sweeps out beams of radio waves like a cosmic lighthouse. Every rotation sends a pulse toward Earth with clockwork regularity. That regularity was the key. When we time those radio flashes, we find they are astonishingly precise. Some pulsars rival atomic clocks. Any tiny change in the arrival time of the pulses means something has disturbed the star's motion. This means pulsars are not just strange stellar corpses, they are also exquisite tools for detecting the slightest gravitational tug. In the early 1990s, astronomer Alexander Wolszczan was observing one such pulsar, PSR B1257+12. Together with Dale Frail, he noticed something odd in the data. The pulses were not perfectly on schedule. They arrived early, then late, in a repeating pattern. The effect was tiny, just milliseconds, but it was consistent. What could cause a city-sized star to wobble in such a delicate, rhythmic way? The only explanation that fit was shocking. There had to be planets. multiple planets in fact, orbiting this dead star, and tugging it back and forth as they moved along their orbits. In the hunt for alien life, this was not the family portrait anyone expected. These pulsar planets were nothing like an Earth-like world around a calm, yellow star. They were super-Earth mass planets packed into tight orbits, some closer to their pulsar than Mercury is to the Sun. Any original atmosphere would likely have been stripped away by the supernova. The intense radiation and particle winds would sterilize exposed surfaces. It should be noted that if any life exists there, it would have to be buried deep under rock or ice, far from the deadly beam. But while these worlds were almost certainly not habitable, their discovery changed everything. By measuring timing variations with extreme precision, Wolszczan and Frail had inferred unseen planets without ever seeing a pixel of them. Indirect detection was not just possible, it was powerful. So it's time to find out the truth. If we could tease planets out of the heartbeat of a dead star, could similar precision techniques reveal planets around ordinary stars like our Sun, where life might actually stand a chance? The next breakthrough would answer that question, and it would come from a subtle wobble in starlight itself. Doppler wobbles, listening for the tug of hidden giants. So if a dead star can betray its planets through timing, what hope do we have with ordinary stars whose pulses are far less regular? To answer that, we have to listen not for a tick, but for a tug. So, let's begin with something familiar. Have you ever heard a siren change pitch as it races past you? As it moves toward you, the sound waves bunch up and the pitch rises. As it moves away, the waves stretch out and the pitch falls. Light behaves the same way. When a star moves toward us, its light is shifted slightly toward blue. When it moves away, slightly toward red. This is the Doppler effect, written not in sound, but in color. Now imagine a planet and a star locked together. They do not orbit the star alone. They orbit a common center of mass, a balance point in space. The planet traces a wide path, but the star also circles, just a little. From far away, that motion is invisible, but its light remembers. The dark spectral lines in the starlight slide back and forth, blueward then redward, in a precise, repeating pattern. This means that by measuring those tiny shifts, we can weigh the unseen companion tugging on the star. In the hunt for alien life, this radial velocity method became our next great tool. It should be noted that the challenge is extreme. For a Sun-like star with an Earth-like planet, the wobble speed is only about the pace of a walking human. Yet in 1995, Michel Mayor and Didier Queloz pushed their spectrograph on the Haute-Provence telescope to this frontier. They monitored a fairly ordinary star in Pegasus, 51 Pegasi, night after night. The data showed an astonishing rhythm, a strong, 4-day cycle in the star's velocity. Something massive was whipping that star around on a blisteringly tight orbit. The best explanation? A giant planet, at least half the mass of Jupiter, circling closer than Mercury does to our Sun. 51 Pegasi b was the first confirmed planet around a Sun-like star, and it was nothing like the worlds in our own system. A hot Jupiter, roasting in a 4-day year, forced astronomers to admit that our ideas about planet formation were incomplete. But while hot Jupiters were shocking, they were also a clue. They were exactly the kind of planet radial velocity is best at finding: heavy worlds, on short orbits, yanking hard on their stars. Optimistically speaking, this was proof the technique worked. Realistically, it revealed a strong selection effect. We were seeing the loudest planets, not the most common. And there was another catch. Without knowing the tilt of the orbit to our line of sight, radial velocity can only give a minimum mass. Is that planet truly a Jupiter twin, or a heavier world seen at an angle? So it's time to find out the truth by combining Doppler wobbles with a different trick: watching stars dim when planets pass in front. Pushing precision from walking speed wobbles to smaller worlds, those dimming events were powerful, but the wobble method was not finished with us yet. Because once we learned to measure a star's motion at the speed of a gentle human walk, the whole exoplanet census changed. Early radial velocity surveys could only see big, close-in worlds tugging their stars by tens of meters per second. That is like trying to study ocean waves but only noticing tsunamis. So, what happens when we start detecting ripples instead? Modern spectrographs, such as HARPS in Chile, HIRES in Hawaii, and ESPRESSO on the Very Large Telescope, pushed precision down to around 1 meter per second, and in some cases even better. This means we can now register a star shifting at roughly walking speed along our line of sight from dozens of light years away. It should be noted that this level of control over starlight is almost absurd. How did we get there? We locked spectrographs in temperature-controlled, vibration-isolated rooms. We used ultra-stable optics, vacuum enclosures, and exquisitely regular calibration sources like laser frequency combs. Every photon was tracked, every drift mapped. In the hunt for alien life, that kind of obsessive stability is not a luxury, it is a requirement, because those tiny changes in wavelength reveal the pull of smaller planets on wider orbits that would have been invisible before. As the precision improved, the catalog of worlds exploded. Hot Jupiters were joined by warm Neptunes, then by super-Earths only a few times our planet's mass. We started finding planets that took weeks, months, even years to complete an orbit, rather than a few frantic days. Optimistically speaking, it felt like the galaxy was overflowing with exotic systems. But while the numbers grew, our picture of what was normal was quietly being distorted. Why? Because radial velocity has very clear selection effects. It is naturally biased toward massive planets close to their star, where gravity is strongest and the wobble is largest. Smaller, Earth-like worlds on year-long orbits barely nudge their stars by 10 centimeters per second, far below what most instruments can reliably see today. So, the early exoplanet zoo, full of hot Jupiters and chunky super-Earths, was never a fair sample of the universe. We were seeing the easiest planets, not the typical ones. This means our first ideas about planetary architecture were shaped more by our tools than by nature itself. If we truly wanted to understand the full diversity of planets, especially the small, potentially habitable ones, we needed a different strategy. Instead of waiting for stars to wobble, we had to watch them flicker. So, let's begin the next step, measuring a dip in starlight so small that an Earth-sized world can betray its presence. And once we do that, the quietest planets start to speak. When stars blink, the transit method's simple, genius trick, when we say a planet can make a star blink, what do we actually mean? It sounds almost mystical, but it is really a simple piece of geometry, pushed to an almost absurd level of precision. Imagine a distant streetlight on a foggy night. Now imagine a single moth flying across your line of sight. The light does not vanish. It just dims by a fraction of a percent for a moment, then returns to normal. If you only glanced once, you would miss it, but if you recorded that streetlight, frame by frame, for hours, you could see the tiny repeating dips and prove the moth was there. This is exactly what the transit method does, scaled up to the level of a star. If a planet's orbit is lined up just right with our line of sight, it will pass in front of its star, blocking a small portion of the starlight. The star doesn't flicker chaotically. It performs a precise, periodic blink. Each transit carves out a tiny notch in the light curve, a shallow valley in the brightness over time. The depth of that valley is the key. This means that by measuring how much the star's light drops, we can infer how big the planet is relative to the star's disk. A giant Jupiter-sized world might block a full percent of the light. An Earth-like planet crossing a Sun-like star hides less than 1 part in 10,000. It should be noted that this is like noticing the streetlight dim by the width of a human hair compared to your entire field of view. Timing matters just as much as depth. The interval between dips tells us the planet's orbital period. Once we know how long it takes to circle its star, Kepler's laws let us calculate the distance of the orbit. Suddenly, from a simple repeating blink, we know both the size of the planet and where it sits in its system. Is it in the Goldilocks zone, or roasting on the inside, or freezing on the outside? In the hunt for alien life, that orbital distance is everything. But while the geometry is simple, the execution borders on impossible. For an Earth-sized planet around a Sun-like star, the signal is smaller than the tiny twinkle introduced by Earth's own atmosphere. Clouds, air turbulence, even day and night all conspire to drown out that 1 in 10,000 dip. Optimistically speaking, we could try from the ground, but the noise would always be whispering over the planet's voice. So it's time to find out the truth about these blinks by leaving our own atmosphere behind. We needed a space telescope that could stare at tens of thousands of stars, unblinking, for years. No sunrise, no weather, just pure, continuous photometry. That is where Kepler enters the story, and with it, the real explosion in our exoplanet census. Kepler's gamble, staring at 150,000 stars for years, so if brief, noisy blinks from the ground are not enough, what happens when we commit to staring? NASA's Kepler Space Telescope was our answer to that question. Instead of hopping from star to star, Kepler locked its gaze onto a single patch of sky in the constellations Cygnus and Lyra, and refused to look away. For years. On its detector sat about 150,000 stars at once, each one monitored for the tiniest, most regular dips in brightness as a planet crossed the stellar disk. This sounds simple, but while the basic idea is straightforward, the execution is brutal. A true Earth passing in front of a sun, like star blocks less than 1 part in 10,000 of the light. that is like watching a lighthouse from thousands of kilometers away and trying to notice when a moth flies across the beam. Any vibration, any cloud, any sunrise would drown that out. So Kepler floated above our atmosphere in its own orbit around the sun, giving us continuous, unbroken data. Continuous is the key word here. In the hunt for alien life, we care deeply about planets with long years, because the Goldilocks zone for a sun-like star is not right up against the fire. You need time to complete a wide orbit. Kepler stared for nearly 4 years in its prime mission, long enough to see an Earth analog transit 3 times, and to watch planets in wider, cooler orbits reveal themselves slowly, one dip at a time. This means Kepler was not just finding hot Jupiters racing around their stars every few days. It was sensitive to smaller, more temperate worlds, including potentially habitable planets around stars similar to our own. It should be noted that this was a statistical mission by design. Kepler did not promise us beautiful images of each planet. It promised us something more abstract, but more profound, a census. And that census was shocking. Instead of a few lucky detections, Kepler delivered thousands of planet candidates, and eventually thousands of confirmed worlds. When astronomers crunched the numbers, correcting for the ones Kepler would have missed, a clear message emerged. On average, most stars in the Milky Way host at least one planet. Planets are not rare jewels, they are the default. Even more surprising was how these systems were arranged. Kepler revealed stars with 5, 6, even 7 transiting planets, packed in tight, with orbits measured in days or weeks. Many of these planets formed resonant chains, where their orbital periods fall into neat ratios, like musical chords repeating around the star. Compact systems of super-Earths and mini-Neptunes crowded close in, utterly unlike our own solar system, where small rocky planets hug the star and giants live far away. Optimistically speaking, this diversity is good news for life, but it also raised new questions. Kepler's light curves told us sizes and orbits, and they let us count how common different types of planets are. Yet for most of these worlds, we still did not know their masses, their compositions, or whether any kind of atmosphere wrapped around them. Kepler had given us the statistics. To move from numbers to actual, characterful planets, we would need new techniques and new telescopes to fill in everything its beautiful, relentless stare could not see. Tests in the nearby neighborhood, planets in our cosmic backyard. Kepler had given us the census, but if we wanted to actually meet our planetary neighbors, we needed something very different. So, let's begin the next chapter with a simple question. What happens if, instead of staring at one tiny patch of sky, we sweep almost the entire sky for nearby worlds? That is exactly what NASA's TESS mission set out to do. While Kepler focused on a single deep field, TESS spreads its gaze across almost the whole celestial sphere, tiling the sky sector by sector. It should be noted that TESS is not hunting faint, distant stars in the galactic suburbs. It is deliberately tuned to bright, nearby stars, the ones close enough that, in the hunt for alien life, we can follow up in exquisite detail. But while Kepler patiently watched the same stars for years, TESS usually stares at a given sector for only about a month, sometimes up to a year near the ecliptic poles. This means its transit search is naturally biased. Short observing windows favor planets that whip around their star quickly, completing an orbit in just days. At first, that might sound limiting. How can such scorched, close-in worlds ever be habitable? Here is where small, cool stars change the story. Around a red dwarf, the Goldilocks zone huddles close to the star. A planet can be in a potentially habitable orbit and still circle its star in just a few days or weeks. TESS is remarkably good at finding exactly these systems, where an Earth-like world does not need a year-long orbit to sit in the right temperature range. The strategic advantage is enormous. Bright, nearby stars give us far more photons to work with. This means radial velocity wobble measurements become easier, letting us weigh the planets and break the degeneracy between size and mass. It also means that when a planet passes in front of its star, starlight filtering through its atmosphere is strong enough for our largest telescopes to dissect. Optimistically speaking, TESS is building a catalog of planets made to be studied, not just counted. We now have super-Earths and sub-Neptunes like TOI 700d, a temperate world in the habitable zone of a red dwarf, and TOI 270's tightly packed system, all flagged as prime targets for the James Webb Space Telescope. Some TESS discoveries already show hints of clouds, escaping atmospheres, or unusual densities that challenge our simple categories. So it's time to find out the truth. Now that we can find thousands of planets and map their sizes and orbits, how do we go beyond silhouettes and orbital periods? How do we turn these light curves into weather, chemistry, even potential signs of life? The next step in our story asks a much harder question. What are these worlds actually like, up close? Beyond counting planets, why detection methods shape what we see. To answer that harder question, we first have to admit something slightly uncomfortable. We have been looking at a very biased sample of worlds. Our tools do not just find planets, they choose which planets we see. So, let's begin with the workhorses. The first method, radial velocity, watches a star's spectrum for a tiny Doppler wobble as an unseen companion tugs it around. This means it is naturally most sensitive to massive planets huddled close in, racing around their star in just a few days. A hot Jupiter produces a big, fast wobble. An Earth-like world at 1 AU barely nudges the star at all. The second method, transits, times those delicate dips in starlight when a planet crosses the stellar disk. Again, the deck is stacked. Big planets block more light, short orbits give more frequent transits, and the orbit has to be lined up almost perfectly with our line of sight. It should be noted that if our own solar system were randomly oriented, most distant observers would never see Earth transit the Sun. But while these methods are exquisitely powerful, they created a distorted first impression. In the early 2000s, our catalogs were suddenly full of hot Jupiters, giant planets skimming their stars in just a few days. Then, with Kepler, super-Earths and mini-Neptunes with short orbits flooded in. Did this mean most planetary systems in the universe are dominated by these extreme worlds? Or were we simply finding what our instruments were best at catching? In the hunt for alien life, that bias matters. Truly Earth-like planets and Earth-like orbits sit in a frustrating sweet spot, small, dim, and slow. To see one full orbit, we need years or even decades of data. To pick out its signal, our measurements must be stable to a few parts in a billion. Optimistically speaking, we are just now reaching that regime for the very nearest stars. So astronomers pushed beyond the big two methods. Direct imaging blocks the glare of the star and chases the faint glow of young, hot giants far from their suns. Microlensing uses gravity itself as a lens, briefly brightening a background star when a hidden planet passes in front. Astrometry tracks a star's position on the sky for a slow, graceful wobble. Timing variations, especially in pulsars and tightly packed systems, reveal planets through tiny shifts in the ticks of cosmic clocks. Here is the pattern interrupt. Some of these techniques have already delivered scenes that look like pure science fiction, actual pictures of glowing, newborn giants circling bright stars, hints of exomoons and rings buried in timing residuals, and cold, distant planets we would never see by transits alone. But to understand what those atmospheres are made of, and whether any of these worlds could be habitable, we need yet another leap in technique. That is where the next part of our story leads. Direct imaging, photographing alien worlds in starlight's glare so if timing tricks and tiny dips in starlight can reveal invisible worlds, what about something more direct? What would it mean to actually take a picture of another planet hanging next to its star on the sky? This sounds simple. We point a telescope, we snap an image, we meet an alien world, but while that is the dream, the reality is brutal. A typical planet is up to 1 billion times fainter than its star, and it sits right next to that glare at a minuscule separation. It should be noted that, from light years away, even Jupiter would look like a firefly buzzing around a searchlight. So, how do we turn down the star without erasing the planet? One approach is the coronagraph. Inside a telescope's optics, we literally block out the central star with a tiny mask, then use carefully shaped mirrors and algorithms to cancel the leftover starlight. This means the surrounding darkness is suddenly deep enough that a faint companion can emerge. On the ground, we pair this with adaptive optics, rapidly flexing mirrors hundreds of times per second to correct the blurring from Earth's atmosphere and sharpen the image. There's also an even more dramatic idea, the starshade. Imagine a giant flower-shaped screen flying tens of thousands of kilometers in front of a space telescope, lining up perfectly with a distant star to cast a carefully sculpted shadow. In the hunt for alien life, that shadow could be the difference between featureless glare and a clean, black stage where planets finally step into view. So what have we actually seen so far? The showpieces are young, massive gas giants, still hot from their formation and glowing strongly in the infrared. The HR 8799 system, for example, gave us the first family portrait of 4 giant planets directly imaged around a single star. They orbit far from their star, tens of astronomical units out, where the angular separation is just large enough and the starlight just manageable. But while these images are spectacular, they reveal our current bias. Direct imaging today favors big, hot, widely separated planets around young stars. True Earth-like worlds in a Goldilocks zone, especially around sun-like or red dwarf stars, are far too faint and too close in to tease out from the glare with present technology. Optimistically speaking, imaging an Earth twin with oceans, clouds, and maybe even continents is a challenge for the next generation of space observatories. So, why struggle so hard for a picture? Because direct imaging does not just detect a planet, it lets us spread its light into a spectrum. From that spectrum, we can probe the atmosphere, measure temperatures, infer clouds and hazes, and one day search for combinations of gases that might hint at life itself. So it's time to find out the truth about what those spectra can already tell us, and how close we are to reading the chemical fingerprints of alien skies. Gravity's magnifying glass, microlensing, astrometry, and subtle shift spectra can tell us what a planet's atmosphere is made of. But what about planets whose light we never see at all? How do we find worlds that never transit, never glow, and barely tug on their star? So, let's begin with one of the strangest tools in our kit, gravitational microlensing. When a foreground star drifts exactly in front of a background star, the foreground star's gravity bends and focuses the background light. For a few days or weeks, that distant background star brightens in a smooth, symmetric curve. This means gravity itself is acting like a lens, a natural telescope built into the fabric of the universe. Now add a planet. If the foreground star has a planet in orbit, its gravity briefly distorts that smooth brightening. For a few hours, sometimes just minutes, the light curve sprouts a sharp spike or a small dip. That tiny, one-time anomaly is the planet's fingerprint. We never see the planet or even its host star clearly, but from that warped flash of light, we can estimate the planet's mass and separation. It should be noted that microlensing is uniquely sensitive to planets at moderate distances from their stars, roughly where Jupiter or Saturn would orbit in our own system. It also works well for low-mass planets, even down to Earth-like or smaller. And because it does not rely on the planet orbiting a visible star at all, microlensing has revealed candidates for free-floating planets, worlds that drift through interstellar space without any sun. In the hunt for alien life, these lonely, starless planets might seem hopeless, yet they tell us how often planetary systems are disrupted and how dynamic the galaxy really is. But while microlensing catches brief, unrepeatable events, astrometry plays the long game. Here we measure a star's position on the sky with absurd precision, year after year, looking for a tiny side-to-side wobble. If a massive planet orbits that star, the star itself traces a small ellipse in the sky. This method is especially powerful for long-period giant planets, the analogs of our Jupiter, which hardly affect transits, but slowly pull their star around over decades. Then, there are timing methods. Beyond the exotic case of pulsars, we now use transit timing variations in multi-planet systems. If one planet tugs on another, its transit will not be perfectly on schedule. Some transits arrive a few minutes early, others a few minutes late. From that subtle dance, hidden planets emerge. Optimistically speaking, each of these techniques has found fewer planets than the big players like transits and radial velocity. Yet together, they fill in the missing pieces. Cold giants far from their stars, low-mass planets in wide orbits, even possible rogue worlds. Without them, our map of planetary architectures across the galaxy would be deeply biased. So what happens when we combine all of these methods and ask a dangerous question? What kinds of planets are we still completely blind to? From dots to worlds, measuring mass, size, and what they're made of. So, what do we actually know about a planet when we first detect it? Often, the uncomfortable answer is, not very much at all. A transit only tells us how big the planet's shadow is. Radial velocity, the Doppler wobble, only tells us how hard the planet pulls on its star, and even then we usually get just a minimum mass. But while each method alone leaves us with half a picture, together they do something almost magical. We can weigh the planet, measure its size, and from that calculate its bulk density. This means we can go from a mysterious dot to a world with a physical nature. Why is density such a powerful clue? Because rock, iron, ice, and hydrogen gas all pack very differently. A small planet with a high density is probably a compact, rocky, terrestrial world. Push the density even higher, and you may be looking at an iron-heavy super-Mercury stripped of lighter material. At the other extreme, a huge planet with a surprisingly low density must be dominated by hydrogen, helium, or puffed-up layers of hot gas. In between, moderate densities hint at volatile rich super-Earths or mini-Neptunes, with deep envelopes of water, ices, or thick atmospheres. Some of the most dramatic surprises in the hunt for alien life have come from this simple mass-radius trick. Take the ultra-puffy hot Jupiters, worlds as large as or larger than Jupiter, yet with densities closer to balsa wood. Their transits scream big planet, but radial velocity reveals that they barely weigh anything for their size, so their atmospheres must be hugely inflated by intense starlight. On the other side, we have dense, iron-rich supermercuries, where the radius looks modest, but the mass is enormous, implying worlds with metallic cores dominating their volume. When we plot thousands of planets on a mass-radius diagram, patterns leap out. One of the clearest is that super-Earths and sub-Neptunes, with sizes between Earth and Neptune, are everywhere. It should be noted that our own solar system has none in this range, which makes our local neighborhood look strangely incomplete. Optimistically speaking, that might mean there are many planetary architectures out there that are more typical than ours, scattered across the Milky Way. Pattern interrupt for your intuition. We started this story with mere dips in starlight and tiny stellar wobbles. Yet now we can say, with confidence, this planet is mostly rock, where this one is a bloated gas-rich world. So it's time to find out the truth about the next step. Beyond bulk density, how can we possibly know what the air is like on these planets, their temperatures, their clouds, or even whether their chemistry hints at life in the Goldilocks zone around their star? So, let's begin to turn silhouettes into living, breathing climates. Reading alien skies, transit spectroscopy and secondary eclipses. If all we see is a tiny dip in starlight, how can we ever read the weather on a distant planet? In the hunt for alien life, this is the moment where simple shadows turn into detailed alien skies. The key idea is surprisingly elegant. When a planet passes in front of its star, most of the light is blocked by the solid body, but a razor-thin ring of starlight skims through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb different colors, leaving behind a pattern of missing wavelengths. These are spectral fingerprints, and they can whisper water vapor, methane, or sodium across light years. So, how do we isolate that whisper from the roar of the star itself? We take the star spectrum before the transit, then again while the planet is crossing. Subtract one from the other, and what remains are tiny, wavelength-dependent changes caused by the atmosphere's absorption. This means a barely perceptible extra dip at one color can reveal a high layer of sodium gas. A bump at infrared wavelengths might betray water vapor or carbon dioxide. It should be noted that these signals are often just a few parts in 10,000, yet with enough data, they become clear. This is transit spectroscopy, and it has already transformed hot Jupiters from anonymous points into worlds with puffy, extended atmospheres, hazes, and even patchy clouds. But there is a second trick, one that sounds almost like cheating. When the planet moves behind the star, it briefly disappears. And during that secondary eclipse, the combined light of star plus planet drops by exactly the amount of the planet's own emitted and reflected light. By comparing the total light just before eclipse and during eclipse, we can isolate the planet's dayside glow. Suddenly, we are not just seeing what the atmosphere blocks, we are seeing what it radiates. In infrared, that drop tells us the dayside temperature. Spread across wavelengths, it becomes an emission spectrum, revealing molecules that shine rather than absorb. For worlds roasting close to their star, secondary eclipses have shown daysides of over 2,000 degrees, with thermal inversions and glowing carbon monoxide. Go one step further, and we do not wait only for transits and eclipses. By watching the system's brightness continuously over an entire orbit, we build a phase curve, a map of how the light changes as different longitudes rotate into view. The hottest point might be shifted east of the substellar point, implying fierce winds that drag heat around. Night sides may be cooler than expected, hinting at poor heat transport or thick, reflective clouds. Optimistically speaking, phase curves are the first crude weather reports on alien worlds, and with Hubble and Spitzer paving the way, and JOS now supercharging all of these techniques, exoplanets stop being mere detections and become physical worlds, with chemistry, climate, and perhaps, in the Goldilocks zone, conditions for life that we will probe even more directly in the next step. Jidwist and the New Era, dissecting light from distant worlds, but what happens when we finally get a telescope that can truly dissect that light, photon by photon? In the hunt for alien life, this is where the game changes. Enter the James Webb Space Telescope. JWST is not just another observatory, it is a superlative infrared machine parked 1.5 million kilometers from Earth with a gold-coated mirror over 6 meters across. That huge mirror gathers far more light than Hubble, and its ultra-sensitive instruments spread that light into fine rainbows across a wide wavelength range, from the glowing heat of hot Jupiters to the faint warmth of small, cool worlds. Why infrared? Because many of the key molecules for life and climate leave their fingerprints there. Water vapor, carbon dioxide, methane, carbon monoxide, even more exotic chemicals, all carve distinctive patterns into a planet's spectrum. Juice stability means it can stare at a star-planet system for hours without drifting, while its spectral resolution lets us see tiny wiggles in the data that older telescopes would simply blur away. This means we can now detect atmospheric features that were previously buried in noise. So, let's begin with what it has already shown us. Some of DREST's first exoplanet targets were hot Jupiters, giant planets hugging their stars in tight orbits, roasted to thousands of degrees. On worlds like WASP-39b, JWST has revealed detailed spectra showing water, carbon dioxide, sulfur dioxide, complex hazes, and clouds high in the atmosphere. These are not vague hints. We see structured features that tell us about chemistry, winds, and even how starlight is reshaping the planet's upper layers. But while hot Jupiters are dramatic, the real excitement comes from smaller, cooler planets. DREST is now turning its gaze to worlds around red dwarf stars, where the Goldilocks zone is close in and transits are frequent. It should be noted that these planets are faint and challenging, yet we are already getting first glimpses of whether they have thick atmospheres or are bare rocks, whether they trap heat efficiently or bleed it into space. How does this connect to habitability? DREST cannot show us continents or oceans, and it cannot, by itself, prove that life exists. What it can do is identify promising atmospheres, measure greenhouse gases, estimate surface temperatures, and test whether some rocky planets manage to hold on to temperate protective air instead of being stripped by their star. Optimistically speaking, it is our first real tool for sorting the merely interesting from the truly potentially Earth-like. So it's time to find out the truth. With DREST blazing the trail and new missions on the horizon, how close are we to finding an actual Earth 2.0? And what, from light years away, would really count as a convincing sign of life? The answer may be stranger and harder to interpret than we expect. The habitable zone trap. Why just right isn't so simple so, if the answer is stranger than we expect. What about the very first question we usually ask? Is the planet in the habitable zone? We hear that phrase so often that it starts to sound like a verdict. Habitable zone? Case closed. Life is possible. But while the term sounds simple, the reality behind it is much more fragile. In its classical definition, the habitable zone is just geometry and energy, the range of distances from a star where an Earth-like planet with an Earth-like atmosphere could keep liquid water on its surface. Too close, and water boils away. Too far, and it freezes. That is all. No guarantee of oceans. No guarantee of clouds or continents. Just the potential for liquid water if everything else cooperates. This means being in the Goldilocks zone is necessary, but absolutely not sufficient. For a world to be truly habitable, a planet could sit perfectly in the middle of that zone and still be a frozen snowball if its atmosphere is too thin, or a runaway greenhouse if its atmosphere is too thick. It should be noted that magnetic fields, rotation rates, and active geology all matter as well. Without a magnetic shield, a star's particles can strip the atmosphere. Without plate tectonics or volcanism, you may not recycle carbon dioxide and water over billions of years. Here is the pattern interrupt. Our catalog of habitable zone planets is heavily biased from the start. In the hunt for alien life, we are not seeing a fair sample of the galaxy. Our main detection tools, radial velocity and especially transits, are best at finding planets that orbit close to their star and pass frequently in front of it, and they work best when the star itself is small and dim, so the planet's signal stands out. This is why so many of our most famous habitable zone candidates orbit red dwarf stars, not sun-like stars. Around a cool red dwarf, the Goldilocks zone is drawn in tight, with orbital periods of days to weeks instead of years. That means more transits, deeper dips in light, and far better data for us. But while this is great for detection, it complicates habitability. Young red dwarfs can spend hundreds of millions of years in a hyperactive phase, blasting their planets with flares and high-energy radiation. Close-in planets are often tidally locked, showing one face to the star forever. Their dayside may bake, while the nightside freezes, and repeated flares can erode or completely strip an atmosphere. Optimistically speaking though, these same systems are still our best current laboratories. A small star makes an Earth-sized transit deeper, and any atmosphere easier to probe with telescopes like Doublest. So it's time to find out the truth. Are we just seeing the easiest planets, or the most promising ones? To answer that, we have to look beyond orbits and into the actual air of these distant worlds. Earth 2.0? How our tools quietly rig the game, but what if the most perfect Earths are already out there, and we have quietly designed our tools so we almost never see them? In the hunt for alien life, that is a disturbing possibility. Let's imagine the true prize, an exact Earth twin. Same size, same un-year orbit around a sun-like star, sitting calmly in the Goldilocks zone. On paper, that sounds like the easiest kind of habitable planet to think about. After all, life arose here. So, surely that is what our telescopes are best at finding, right? But while that feels intuitive, the reality is almost the opposite. For a planet like this to transit, its orbit has to be lined up just right. The chance is only about 1 in 200, and even if we get lucky, that tiny world blocks less than 1 part in 10,000 of its star's light for just a few hours, once a year. Miss one dip, and you wait another entire year for the next clue that the planet even exists. It should be noted that radial velocity, the wobble method, does not rescue us here either. An Earth tugging on a sun shifts the star at roughly 10 centimeters per second. That is slower than a walking human. Our best spectrographs are only now approaching that precision, and real stars are noisy, with magnetic cycles and spots that mimic or hide such faint signals. This means mission lifetimes quietly rig the game. Kepler watched its original field for about 4 years. To be confident in an Earth-like orbit, you want at least 3 clean transits, that is 3 years minimum, with no gaps, no flares, no instrumental issues. Many candidates only show 1 or 2 dips before the mission ends, leaving us with tantalizing but unconfirmed Earth analogs. So the catalog we celebrate is not a neutral map of the universe. It is a map of what our instruments like to see. Short-period planets that whip around their star in days. Super-Earths and mini-Neptunes that block more light. Worlds around small, cool stars, especially a red dwarf, where the Goldilocks zone is so close and that a year can last only a couple of weeks. Optimistically speaking, this biased sample is still telling us something profound. Statistical studies of Kepler data, correcting for what we miss, suggest that Earth-sized planets in the habitable zones of sun-like stars may be reasonably common. Maybe tens of % of sun-like stars host one. So, it's time to find out the truth. Are we simply looking under a cosmic street lamp, counting the easy, close-seen worlds, while the most Earth-like planets remain almost invisible to our current methods? In the next part, we will see how astronomers try to escape that bias, and what it will really take to uncover a genuine Earth 2.0, future eyes, Roman, ELTs, and the Habitable Worlds Observatory, if the worlds we really care about are almost invisible. What kind of eyes do we need to finally see them? Right now, we have a census of the loudest, easiest planets. The next generation of observatories is designed to find the quiet ones, the true Earth-like needles in the galactic haystack. So, let's begin with a telescope that will not stare, but survey. NASA's Nancy Grace Roman Space Telescope will spend months watching dense star fields toward the center of the Milky Way, waiting for rare alignments. When a foreground star passes in front of a background star, its gravity briefly magnifies the background light. If that foreground star has a planet, the planet adds a tiny extra blip. This is gravitational microlensing in action. Roman's microlensing survey will not just find 1 or 2 curiosities. It should be noted that it is designed to deliver a statistical census of planets at wider orbits, including analogs of Jupiter, Saturn, and even free-floating worlds that no star holds on to. This means, for the first time, we will be able to compare our own outer system to thousands of others, and ask whether our architecture is common or strange. But while Roman looks outward across the galaxy, a different class of instruments will zoom in on our nearest neighbors. Extremely large telescopes on the ground, with mirrors 30 to 40 meters across, are now under construction in Chile and elsewhere, with advanced adaptive optics reshaping their mirrors hundreds of times per second. They will sharpen starlight enough to directly image giant planets around nearby stars, and even some super-Earths just a few times our planet's mass. In the hunt for alien life, direct imaging is powerful because it lets us split a planet's light into a spectrum. From the ground, ELTs will probe atmospheres of young, hot giants and cooler worlds in wide orbits, searching for water vapor, clouds, and perhaps the first hints of complex chemistry. But the real prize, Earth-sized planets in the Goldilocks zone of sun-like stars, will demand something even more ambitious. Enter the Habitable Worlds Observatory concept and related ideas like the proposed Life Interferometer. These future space missions are being designed from the start with one audacious goal: to directly image dozens of truly Earth-sized planets at Earth-like separations, and to analyze their atmospheres for biosignature gases such as oxygen, ozone, methane, and combinations that are very hard to maintain without life. To do that, we must nearly erase the star. Planned high-contrast imaging systems will use ultra-precise coronagraphs to sculpt destructive interference patterns and carve out a dark hole in the star's glare. Some concepts add a separate starshade spacecraft, flying tens of thousands of kilometers away, unfolding a huge flower-shaped screen to block starlight before it even enters the telescope. Optimistically speaking, these tools could let us test, for the first time, whether life is a common byproduct of Earth-like planets or a cosmic fluke. But how do we make sure that a whiff of oxygen or a faint methane signal really means biology and not some lifeless chemistry tricking us? So it's time to find out the truth in the next section. We will explore what counts as a believable biosignature and how close we might be to mistaking a dead world for a living one. Biosignatures and technosignatures, what would alien life look like in data? So if we do see something strange in an exoplanet spectrum, what exactly are we hoping for? In the hunt for alien life, we need more than a single exciting line on a graph. We need patterns that are very hard to make without biology. Those patterns are what astronomers call biosignatures. A biosignature is any observable feature in the light from a planet, certain gas combinations in the atmosphere, unusual surface colors, or even changes over time, that is more likely to be produced by life than by lifeless chemistry. This means we are not just searching for one magic molecule, we are searching for a story written across the entire planet. The classic example is oxygen. On Earth, our atmosphere is about 21% O, constantly replenished by photosynthetic life. Oxygen by itself, though, is not enough. A young star can strip water apart and leave behind a false ocean of oxygen. So, let's begin with context. What we really want to see is oxygen and its cousin ozone existing alongside reducing gases like methane, which should rapidly destroy each other. If they persist together in the same atmosphere, something must be continuously rebuilding that imbalance. But while that combination sounds like a clear sign of biology, nature can be sneaky. Volcanoes, photochemistry, and exotic surface minerals can all mimic parts of the signal. It should be noted that even a strong OOCH mix around a seemingly Earth-like planet would not instantly prove that forests and oceans are thriving there. We would need to know the star's activity, the planet's age, and whether other gases line up with a living, rather than purely chemical, world. Biosignatures are not limited to gases. Future missions may look for a red edge in the reflected light of a planet, a sharp jump in brightness at certain wavelengths caused on Earth by plant pigments. If we saw a similar pigment-like feature rotating in and out of view as the planet spins, it could hint at continents covered in alien photosynthesizers. We might also track seasonal swings in carbon dioxide or methane, or clouds and hazes that wax and wane like weather and growing seasons. Then, there are technosignatures, evidence not just of life, but of technology. These range from narrowband radio signals to excess waste heat from megastructures, from artificial illumination on the night side of a planet to industrial pollutants in the atmosphere that have no known natural source. Imagine detecting chlorofluorocarbon-like molecules, or a night hemisphere that is slightly brighter than it should be. Optimistically speaking, that would be a very loud whisper from a distant civilization. Here is the pattern interrupt. Even with all of this, there may never be a single we found alien spectrum. Instead, we will move step by cautious step, from this is interesting to this is probably biological. In the next section, we will see how upcoming telescopes are being engineered to make those careful judgments possible. Exomoons, rings, and oddities, the next layer of complexity. If even a single spectrum might never be enough to claim life, what happens when the systems we study turn out to be far messier than a simple star and a few planets? In the hunt for alien life, we are now discovering that planet is only the beginning of the story. Just as planets orbit a star, moons orbit planets. That sounds obvious, but it should be noted that this simple fact explodes the number of potentially habitable environments. A giant planet sitting in the Goldilocks zone might be a stormy, unwelcoming world. Yet its large rocky moons could have temperate surfaces, stable liquid water, and thick atmospheres. Think of a scaled-up version of Jupiter in a sun-like system, with several Earth-like satellites. Suddenly, one habitable zone orbit might host a whole miniature archipelago of possible homes for life. So how do we actually find these exomoons when we can barely see their planets? Here the methods we have been using turn into precision tools. If a planet passes in front of its star, the timing of those transits should be clockwork. Add a moon, and the planet wobbles around their shared center of mass. This means each transit arrives a little early or a little late, and its duration stretches or shrinks. On top of that, the moon itself might briefly block a tiny extra bit of starlight, leaving a second, shallow dip in the light curve. Astronomers have reported tantalizing, but still unconfirmed, moon candidates using exactly these tricks, especially around large, distant gas giants. But while moons are the headline act, they are not the only oddities hiding in the data. Rings, like a scaled-up version of Saturn's, could make a planet's transit wider and give it a strange, asymmetric shape. Exocomets, trailing long dusty tails, can produce gradual, lopsided dimmings that repeat irregularly. Circumplanetary disks of gas and dust around young planets can masquerade as oversized worlds, or even as multiple planets blended together. All of these structures can mimic or complicate the clean signals we once hoped for. This is where the real complexity begins. As our telescopes sharpen and our time series grow longer, we are moving from the simple question, is there a planet, to detailed modeling of whole systems, with moons, rings, debris and migrating comets, all interacting. Optimistically speaking, that richness means many more ways for habitable environments to exist, but it also means many more ways to fool ourselves. So it's time to find out the truth. Each new layer we add demands multiple, complementary methods to cross-check what we think we see. In the next part, we will push this even further and ask a harder question. What if the strangest signals are not natural at all? From first wobbles to alien weather reports, the journey so far. So, after all of that complexity, what have we actually learned about our place in the galaxy? We started with almost nothing. Now, we are sketching weather maps of worlds we will never visit. So, let's begin at the beginning. In the 19th century, astronomers were already claiming planets around nearby stars, but the evidence was vague at best. It should be noted that for most of the 20th century, every such claim fell apart under better data. Even famous cases, like Peter van de Kamp's supposed planet around Barnard's star, turned out to be quirks of the telescope, not a real world in orbit. For decades, the universe looked strangely empty. Then the dam broke in the 1990s, in the strangest possible way. The first confirmed exoplanets circled a pulsar, a dead stellar core, sweeping radio beams through space. That system was no place for life as we know it, but it proved the concept: planets could survive extreme violence. Soon after, radial velocity measurements revealed 51 Pegasi b, a hot Jupiter whipping around its star every 4 days. But while that method was exquisitely sensitive to massive, close-in worlds, it was almost blind to small, Earth-like planets farther out. Our first census was badly biased. Transits changed everything. Kepler stared at over 150,000 stars, watching for tiny, periodic dips in brightness. This means we suddenly had radii, orbits, and whole multi-planet systems laid out in the light curves. The result? Planets are common. Super-Earths and mini-Neptunes, which do not exist in our own system, turned out to be everywhere. Our solar system, which we once treated as the template, became just one odd example among many. Tests then turned that revolution toward our cosmic neighborhood, finding transiting planets around bright, nearby stars, including more than a few red dwarf systems. That is why TRAPPIST-1 matters so much. In the hunt for alien life, these close, compact systems are laboratories we can probe in real detail. Along the way, every method opened a different window. Direct imaging picked out young blazing giants far from their stars. Microlensing let us glimpse cold wanderers halfway to the galactic center. Astrometry finally began to see the slow, side-to-side stellar drift from wider orbits. Timing variations around pulsars and in multi-planet systems exposed hidden companions. Optimistically speaking, the message is clear: the galaxy is rich in diverse worlds, and the focus has shifted. We are no longer satisfied with just there is a planet. We combine masses from radial velocity with radii from transits to map out mass, radius relationships, and guess at rock, water, or gas. We read atmospheric spectra during transits and eclipses, trace phase curves as day and night rotate in and out of view, and even build crude temperature maps that let us talk about clouds, winds, and chemistry on distant, potentially habitable worlds. So it's time to find out the truth about the next step. With thousands of planets and detailed atmospheres in hand, how close are we to a real, defensible detection of life? What we still don't know: limits, uncertainties, and the road ahead. So, how much do we really know about these worlds we are so excited about? In the hunt for alien life, this is where we have to slow down and admit just how thin our evidence still is. Most of the time, an exoplanet is not a vivid globe in a telescope. It is 3 or 4 numbers on a plot: radius from a transit depth, mass from a Doppler wobble, an orbital period from repeating dips, maybe a hint of an atmosphere from a barely there spectral line. It should be noted that each of those numbers comes with large error bars and with models built in. Change the model, and suddenly the same planet can look rocky, icy, or wrapped in a deep ocean. This means that when we talk about interiors, we are often guessing. Is that super-Earth an iron-rich world with a thin crust, or a mini-Neptune with a high-pressure water mantle? We do not see the surface. We infer it from bulk density and from theories of how planets form. Surface conditions are even trickier. A planet in the Goldilocks zone could host oceans, or a runaway greenhouse, or a frozen desert, all with the same average amount of starlight. Clouds make things harder again. High clouds can hide lower layers, flatten spectral features, and mimic a clear but thin atmosphere. On a tidally locked world around a red dwarf, cloud decks might pile up on the day's side and change the climate completely. From light curves alone, separating weather from composition, and composition from true habitability is incredibly difficult. So where does that leave biosignatures? Optimistically speaking, we will eventually detect combinations of gases that are very hard to explain without life. But while that is the dream, the reality is probabilistic. Oxygen could come from broken water molecules on a dry world. Methane could leak from geology. We will argue over false positives and false negatives, and we may collect a whole catalog of maybe planets before we see a single case that most scientists are willing to call a strong candidate. Upcoming missions promise to sharpen the picture. JUICE is only the beginning. The Roman Space Telescope, giant ground-based observatories, and future concepts like the Habitable Worlds Observatory or LIFE will push to smaller planets, fainter stars, and finer details. Yet there will always be trade-offs. Every hour spent staring at one promising Earth-like world is an hour not spent surveying a wider system. Instrument designs favor some wavelengths over others. No telescope can do everything. So, let's begin to see this for what it really is: a long-term, multi-generational project. Each decade adds new tools, more precise data, and better models. We are living at the moment when the first real hints of life beyond Earth might become detectable. But what will we actually do if a planet's spectrum whispers maybe and never quite says yes? Are we alone? Your role in the next chapter of exoplanet science maybe, the real question, is not what we will do if a spectrum only whispers maybe. The deeper question is what happens when, one day, it finally screams yes. Remember where we started. If a distant civilization watched our sun, they would see it wobble, ever so slightly, as Earth tugs it in our yearly orbit. They would see tiny flickers as our planet crossed the solar disk. From those subtle clues, from that delicate dance of light and motion, they could infer oceans, an atmosphere, perhaps even the chemical scars of life. In the hunt for alien life, we are now learning to read their stars the same way. This means the thought experiment is no longer just imagination. Radial velocity curves, transit depths, phase curves, spectra, these are our alien astronomer tools. We have turned the entire sky into a laboratory where each star might host a system of hidden planets. It should be noted that only a few decades ago, we did not know if other planetary systems were rare accidents. Now the data are clear. Planets are everywhere. Hot Jupiters, super-Earths, mini-Neptunes, worlds in and out of the Goldilocks zone. The universe builds more planetary architectures than we ever dreamed. Earth is no longer the template, it is one example. So, imagine this. A future telescope isolates the light from a single pale point, an Earth-like planet around a distant red dwarf or sun-like star. We split that light into a spectrum. We see oxygen and methane together, far from equilibrium. We see hints of water vapor, maybe a seasonal pattern as the planet orbits. For the first time, we hold in a single line of colors the most convincing biosignature we have ever seen. What changes in that moment? Our maps of the cosmos would no longer show potentially habitable in cautious quotation marks. They would show at least one confirmed living world beyond Earth. But while that future feels distant, your role in reaching it is not. So, let's begin with something simple you can do after this video ends. Follow the missions that are pushing this frontier. JESS, TESS, CHEOPS, the upcoming Roman Space Telescope, the giant observatories rising on Earth. Support science education in your community. Optimistically speaking, the next generation of exoplanet hunters might be watching this right now. And if you want to go further, you can. Citizen science projects like Planet Hunters and Exoplanet Explorers invite you to sift real starlight, searching for the faint dips that might reveal a new world. You do not need a PhD to help find a planet. You need curiosity, patience, and a willingness to look closely when a star's light stutters. Pattern interrupt. What if the first truly Earth-like world is found not by a supercomputer, but by you on a quiet evening at home? So it's time to find out the truth together. Subscribe if you want to stay with us as we dive into specific systems, from TRAPPIST-1 to the strangest hot Jupiters, and unpack each detection method in detail. Share this video with someone who has ever looked up and wondered if we are alone, because the story of how we find exoplanets and what they are really like has only just begun.